Here's our next example in section 4.4, but this is also going to incorporate some 4.3 stuff as well. We're going to consider the function f of x equals x to the fifth minus 5x to the fourth. And we're going to find the intervals where this function is increasing, where it's decreasing. We're going to find extreme values. We're going to find places where this is concave up, where it's concave down, and we're going to find inflection points if it has any. So we are going to find a lot of stuff for this. First things first, let's start with part A, looking for places where this function is increasing and decreasing. Now that's going to take the first derivative to figure that out. So we should do that. F prime of x is going to be 5x to the fourth minus 20x to the third power. Okay. And we will want to get our critical points from that. So critical, I'll just put CPs. How about that? CPs, critical points. Okay, so the function's derivative f prime of x is never undefined, so we can rule that out. And we just need to look at where f prime of x equals 0. And so that would be 5x to the fourth minus 20x cubed equals 0. And we'll factor out the greatest common factor from both of those terms, which would be 5x cubed. And we're left with x minus 4. And that's it. Okay. Okay, so the critical points that we're going to get here are going to be x equals 0. And then we're also going to get x equals 4. Okay, so those are our critical points. And so now we are going to need to set up a number line to test this. So set up your number line, and we're going to label this with what it's testing. We're testing f prime of x. And f prime of x, let's also put in the equation, or sorry, the function for that. I am going to write it in like this, 5x cubed times x minus 4. I'm going to put it in the factored form there because it just makes the sign analysis a little bit easier. Okay, and put your critical points on there, 0 and 4. F prime of x equaled 0 at both of those places. And then we're going to test some intervals. So remember how to do this with the sign analysis. You just need to see whether the individual factors are positive or negative, and then we'll get a positive or negative result overall. So in this first interval over here on the left, pick any negative number you like to think of. And when you do that, 5x cubed, regardless of whatever your number is going to be negative. And x minus 4, also regardless of whatever negative number you're thinking of, that is also going to be negative. So we got two negatives over there. Two negatives make a positive. So f prime of x is positive when x is less than 0. Then pick some number in between 0 and 4 to think of, maybe 1 or 2, something like that. And your first factor, 5x cubed, will be positive, while the second one is going to be negative. Again, doesn't matter what number you picked. F prime of x overall should turn out to be negative in that interval. And you do the last one here, pick some number greater than 4, and both factors should turn out positive, giving you a positive first derivative. All right, so that gives us a lot of information on that number line there. We can identify where our function is increasing and where it's decreasing. Okay, so our intervals of increase are going to be the positive first derivative places. And so that would be numbers that are less than 0. So as an interval, negative infinity to 0. And then we're going to union with our other interval over here from 4 off to infinity. Okay, so there's where the function is increasing, and then decreasing is just going to be the interval in between those, right here in the middle where the derivative is negative. And so that would be from 0 to 4. Okay, so that takes care of part A for us. We've identified where the function is increasing and where it's decreasing. And then we can also use this information and this number line here to identify our local extreme values. Okay, so that would be your local max and local min. Okay, we'll look at maximum and minimum values. All right, and so we'll look at what happens on either side of our critical points. As we are looking at the critical point here at x equals 0, we can see that the function is increasing, positive first derivative there at first, and then it switches to a negative first derivative, decreasing. So that increase to decrease shape of the function is going to give us a local maximum there. So whatever f of 0 is, that's going to be a local max. All right, now contrary to that, at our critical point here at x equals 4, the function is decreasing at first. And then on the other side of 4, it switches to increasing. And so that shape, decreasing function to increasing function, is going to give us a local minimum at x equals 4. So whatever value f of 4 is, that's going to be a minimum. Okay, now let's check back on our original function here. Okay, because we need to get the function values for that local max, local min. So f of 0, that one's pretty easy to plug in your head. 0 to the 5th minus 5 times 0 to the 4th would just be 0. Okay. And then f of 4 would be 4 to the 5th minus 5 times 4 to the 4th. And when you crunch those numbers, you end up getting negative 256. All right. So that takes care of parts A and B. Increase, decrease, local max and min, you can take care of with the first derivative. Now for the second grouping of parts there, C and D, we're going to need the second derivative to look at concavity and inflection points. So go down here and we'll take our second derivative, f double prime of x, which we can just use the power rule on our first derivative here, take the derivative of that. That would be 20x cubed minus 60x squared. Okay, 20x cubed minus 60x squared for our second derivative. Okay, and we might as well factor this right from the start. We're going to need to do that anyway. Take out that greatest common factor of 20x squared. And then you'd have x minus 3 left over. Okay, note this is never undefined. All right, that tends to happen with a lot of problems here at the start, just because we work with polynomials a lot. All right, so this is never undefined. We just need to see where it equals 0. And I'm going to put PIPs for that, because these are the potential inflection points of the function, where f double prime of x equals 0. All right, 20x squared times x minus 3 equals 0. That is going to give us x equals 0 and x equals 3 for locations of potential inflection points. But we need to see where the concavity actually changes to see if it is actually an inflection point or not. And so we're going to need to test this on a number line. So make that number line, label it with what you're testing. That way we don't confuse this one with the number line for the first derivative because they're different things. Okay, this is the function we're working on here. And we'll put in our points of interest here, 0 and 3. All right, f double prime equal to 0 at both of those. And now let's test. So sign analysis on this again. Pick some negative number, any negative number. 20x squared is going to turn out to be positive. And then you take your negative number and subtract 3, and that factor would be negative. So negative second derivative over there. Now pick some number in between 0 and 3. 20x squared would be positive for that. 20x squared actually is positive anywhere because of the x squared. Interesting. And then if you picture that number between 0 and 3, I'm thinking of the number 1, by the way. You might be thinking of 2 or something else, some decimal even, whatever. Whatever your number is, if you subtract 3, it's going to be a negative result. So we still have a negative second derivative in that interval. Pick some number bigger than 3. 20x squared is still positive, but now x minus 3 is positive as well. So we get a positive second derivative in that part. Okay. So from that, we can identify the different types of concavity. That was question part C. C for concavity. Hey. Okay. So this function is going to be concave up. Okay, up is the positive, happy type. So concave up would just be where we have this positive second derivative there, the interval from 3 to infinity. Okay, and then concave down. There's actually 2 different ways you could say this. It's going to be concave down where we have a negative second derivative. So you could either say that as it's the interval from negative infinity all the way up to 3. Okay, because that would cover everything through here. Okay, all the way up to x equals 3. Or you could list that as the 2 different intervals. You could say negative infinity to 0 and then 0 to 3. I'm fine with either one of those. I think my math lab might favor the second type. I think my math lab also doesn't want you to use the union symbol, so you could just put a comma there instead, however they ask you to format it. But I'm pretty sure when you're doing your homework, you might want to try this format to start out with. But I'm okay with either one of these on exam questions. Okay, so there's areas where this is concave up and concave down. Okay, concave up, down, and down. And so for the last part, we were to identify the inflection points, if there are any. And we do happen to have one inflection point here. See if you can spot where that is. Okay, so an inflection point is where the function changes concavity. I was going to say shifts concavity, but changes makes more sense there, I think. So we only have a change in concavity around x equals 3, where it goes from concave down to concave up, x equals 0 is not an inflection point. Even though we found it in the same way, that's why these are potential inflection points. These are not guaranteed inflection points, because x equals 3 is an inflection point and x equals 0 is not. So you got to really make this number line and actually test the concavity. So an inflection point will be at x equals 3. And so then you could find the function value at that point. F of 3, let's see, what was our function doing again? Okay, 3 to the 5th minus 5 times 3 to the 4th. Okay, when you do that, you'll get a y value of negative 162. Okay, so we found everything to do with the second derivative here, concavity and inflection points. Now, the one last thing I want to tack on to this example is to look at a graph of this function. Okay, x to the 5th minus 5x to the 4th. And I did graph this one in advance so I could play around with the window a bit. As you can see, like here, we get some pretty large negative y values. So let me pull this guy in. Ta-da! That's the function. All right. So this is f of x. X to the 5th minus 5x to the 4th. And let's just run through and see all the things that we identified based on our derivatives here. So based on our first derivative, we said that the function was increasing from negative infinity to 0 and 4 to infinity, and then decreasing from 0 to 4. Let's check out those intervals on the graph. Okay, so let's zoom out a bit here. All right. So from negative infinity to 0, that would be this portion of the x-axis. You can see that, yes, the function is actually increasing on that interval. Yay. And then it's decreasing from x equals 0 to x equals 4, which is right here. That right there, that's 4. Okay, so decreasing, check. And then from 4 to infinity, that would be here. And we can see that, yes, the function is increasing again on that interval. So check, check. Now for our local maximum, there was a local maximum at the origin, 0, 0. And yeah, there actually is. It's at the top of that kind of flattened hill type of shape, 0, 0, local max. And then we have a local minimum at 4, negative 256. And that's why I had to mess with the axes on this. So here's x equals 4, and then negative 256 is right about there. Okay. We're between negative 200 and negative 300. So yeah, that makes sense. So we can see our local minimum right there. So everything is matching up so far. That's great. Now, if we look at our intervals of concavity here, we said that this function was concave up from 3 to infinity. All right, so 3 is 1, 2, 3 right here. All right. And so that would mean, yeah, we have a concave up type of shape on our function from 3 to infinity. And yeah, you can see that happy face type of U shape for the concave up, positive second derivative. on the graph right here. Okay, and it shoots off. All right. So there's concave up and then concave down on the other interval from -infinity to 3, or you could say the split version of that, remember. But yeah, we see that concave down, frowny face type of shape over there. And so yeah, we have the right concavity on our graph. And then the inflection point, yeah, is only at x equals 3. That's the only place our concavity changes. And so that right there is an inflection point. All right, at 3, -162. Well, you know, the y value, it's a little hard to tell because the y-axis is on such a large scale, but that looks approximately in the right place there. So everything truly matches up. All this information that we got from the first and second derivatives, we can see all of that reflected in the graph. And that's the type of thing we're going to be looking at for the rest of the section here, is building graphs based on information from the first and second derivatives. So we're not going to be given this graph, we are going to come up with it ourselves.